Hello everyone. I'm Nusret and I'm very happy to be here and be presenting our work, batch decryption without epochs and its application to encrypted mempools. This is joint work with Dan Bonnet and Evan Lofer from Stanford University, and this was work done while I was at Stanford. And without further ado, let's get going. Okay, some important disclaimers because I'm now currently at A16Z crypto research. Yeah, so skip that. Okay, so the main motivation for this work will be maximal extractable value, or MEV for short. To understand what MEV is, let's consider a model of blockchains with a blockchain that is built by a set of nodes called the validators, here denoted by this computer, and a set of users called the clients that send transactions to the blockchain. So what happens under the hood when a client sends a transaction to the blockchain is that the transaction first goes into the pool of transactions called the mempool. Then the validators who is responsible for building the next block selects a subset of these transactions to include in its block, right? Now, this validator who is going to create the next block has a lot of power when it comes to the ordering of the transactions in its block, or like when it comes to selecting or excluding certain transactions. And now it can exploit this power to extract revenue or profit from some of these clients' transactions. And here we have a victim transaction that's going to be targeted. And what this malicious block builder is going to do is that it's going to insert its own transaction right before the victim's transaction to basically capture some revenue that would have otherwise gone to the victim. For instance, if the victim was going to buy something, then the front-running transaction can buy the same item in advance and drive up its price, causing the victim to buy it at a higher price. And the adversary can maybe later use the fact that it bought the item at a smaller price. Right, and then these types of attacks can come in various forms. It can be front running and back running, or even sandwiching a transaction. Okay, so these attacks crucially rest on the fact that the block builder knows the content of the client's transaction. Because in this example, the client was buying something. What if it was selling something, right? Now, if you front run a client that is selling something, that is not very useful. You want to be after the selling party, not before the selling party. So one idea to combat such attacks could basically be having the clients encrypt their transactions before sending them to the mempool. Now, the adversary wouldn't know the content of the transactions, and then it will basically have to order this random looking strings and then get it confirmed before it even get a sense of what the transaction is doing. Okay, so far so good. Now, there's this problem of under what key these transactions are encrypted though, right? So let's do a thought experiment. Suppose they are encrypted under a symmetric key encryption scheme. Then what happens is that the client needs to come later. Once the transactions are ordered and confirmed as part of the blockchain, the client needs to come back and decrypt it. We don't want that because that's like back and forth with the clients. Furthermore, the client itself can be malicious and then might never decrypt that transaction. And that will be like a data availability issue for the blockchain. So, okay, symmetric key is not good. Okay, now let's go to public key. But then whose public keys these transactions are encrypted, right? So let's go through a few examples. So the one such example could be threshold decryption. Here we have a set of validators who are basically executing this consensus protocol for the blockchain. And then the clients are going to encrypt their transactions under a different public key per block in this idea. Okay, so this is the ciphertext for the transaction, and PKI is the public key for block I. Now, once block I is confirmed, T out of these N validators will basically publish shares of the secret key for this public key of block I. And if T out of N correctly publishes their secret key shares, then these secret key shares can be combined to obtain the secret key for corresponding to the public key of block I and decrypt all of the transactions that are inside block I. However, there is an issue with this. What is the issue? Suppose I sent a transaction to be included in block I, right? But the block I didn't make it into the block I. It was left in the mempool. Now, once this secret key is revealed, anyone will also be able to decrypt my transaction, even though it's still in the mempool. So this solution does not provide mempool privacy. So it's no good. Okay, now there are ways around that. That's the second idea. Why don't we, instead of publishing shares of the secret key, why don't we publish decryption shares? Now, in this idea, clients encrypt their transactions under a single public key. Okay. Now, the validator is going to publish decryption shares for decrypting each ciphertext corresponding to a transaction after the block is confirmed. Okay, so and then combining these decryption shares, you will be able to obtain the plaintext transaction for each transaction inside the confirmed block. Okay, is this solution clear? This is not publishing shares of the secret key, but it's publishing decryption shares per ciphertext, meaning per transaction. But now there is a communication issue here. The communication blows up quite a bit because suppose there are L transactions in the block, and each validator needs to publish a decryption share for each of the transactions in the block, which means there will be in total n times L decryption shares being published. So this is a lot of communication. Now, this basically begets the question, can we design a scheme where only the L transactions in a block be decrypted by a single small decryption key? Okay, so this is the main motivating question for this work. Are there any questions so far? Okay, so now I will capture this goal that I expressed as a question in a primitive, and then but building up to this primitive, let's do a warm-up exercise, and then what the primitive is doing will be very clear. So the warm-up is I would like to cover something called identity-based encryption. So identity-based encryption is a fancy public key encryption scheme where the public keys can be any string. So it's characterized by 4 algorithms. The setup algorithm outputs a master public key and a master secret key. In the encrypt algorithm, you encrypt your message, which is this transaction, under an identity that you pick, right? It could be anything, your email, your address, whatever. So this identity basically acts as this random public key that you can pick. Now, there is a derivation algorithm which takes the master secret key and identity and derives a secret key for this identity. And then with the secret key derived for the identity and a ciphertext created under that identity, you can obtain the plaintext transaction. So this is identity-based encryption. Now, it needs to satisfy correctness. Decryption for a ciphertext created under identity R must succeed given a secret key derived for identity R. And security in formula should be that messages encrypted under some identity R should remain hidden if no secret key derived for that identity was ever published. Okay. Now, let's do another thought experiment. Can we just use identity-based encryption to solve our problem? Well, I think I revealed the answer already, unfortunately. How would you use this? So you would have maybe clients encrypt their transactions to an identity you pick, send them to the mempool, then these transactions get included in a block, and then the validators, they publish, let's say, shares of the secret key derived for the identities picked for the transactions of the clients. But still, there are like L transactions, meaning there are L secret keys derived for L identities. And if each validator is publishing a share of each of these L identities, still N times L communication, which is a lot. So this does not solve our problem, but it gets us almost there, because what we are actually after to solve our problem is batch decryption. And I would like to model today that problem as a batch IBE problem. So if you look at these algorithms, it's almost the same as like the IBE primitives, except that now I am going to be generating a single succinct decryption key for a batch of identities. Okay, so here is the batch of identities. These are the batch of identities of the ciphertext included inside the block. And then decryption will basically take a batch of ciphertexts which are in the block, and then this single succinct decryption key, and then it will output the plaintext transactions. And now I will only have to, these validators will only have to post a share of the single succinct decryption key, which makes our total communication order n, which is the best you can do all validators are talking. Our security properties should be, again, correctness, meaning decryption should succeed for any ciphertext in a batch, given a correct decryption key for that batch. And then security says if you encrypt a message under some identity, the message should remain hidden. If no decryption key for a batch, including the identity of that message, was ever published. Okay? So are there any questions about the primitive? So this is what we will be going after in the talk. Hopefully this was enough motivation. Okay, now, of course, people have asked this problem before, and I would like to cover what they thought about and what they figured out. So now our goal is basically, or the way, okay, so the way this problem was approached by past works is they were publishing an IBE secret key. Now, I don't want to publish the IBE secret key for a given identity, but I want to publish it for a batch of identities, right? I want to get a decryption key for a batch of identities. So why don't we instead publish a secret key for a commitment to a batch of identities? So this was the main idea that drove the past work. And then in these past works, for the IBE, they use the Bonnet-Franklin IBE, identity-based encryption. And for the committing to the batch of identity tags, they use the KZG commitments. Now, if you know a little bit about these identity-based encryption schemes, their secret keys derived for identities are essentially like signatures. So the decryption key for this line of work was basically the BLS signature on the KZG commitment to the identities. So this is how the decryption key looked like. And then how you encrypt it in these past works was that now I'm taking a very high level look on them, but like they would use witness encryption for a linear constraint system. By linear, I mean linear in your witness. And in this case, your witness is the commitment to the batch of identities, because when you're encrypting, you don't know what your batch you will be included in looks like. So it's witness. And then the witness also includes the decryption key. And then this witness encryption scheme for the linear constraint system should basically encode the following two checks. The first one is the verification that an identity is among those committed by the KZG commitment. Now, if you know how the KZG opening proof verification looks like, this is actually a linear relation in our witness elements being the KZG commitment C. Identity tag is public because if I'm the encrypting guy, I know, of course, what identity tag I picked, but I don't know my opening proof. That is, again, part of the witness. But again, in the opening proof and the KZG commitment, this is a linear relation. I never pair two witness elements here. And then BLS signature verification, it looks like this, as you see on the screen. You hash the KZG commitment and you multiply it with, so you pair it with the public key, and you check if it is equal to the pairing of the decryption key, which is the BLS signature on the KZG commitment. But now here is an issue. Is this a linear check? Is it linear in C and SBK? It's not linear, right? Because there's a hashing here, which you would model as a random oracle. So this is nonlinear. And then to make this linear, what these earlier works did was they basically replaced the hash with a random shift in the group. And this B is the random shift. But now when you replace the hash with a random shift, you take a BLS signature, and in some sense, you make it a one-time BLS signature. And because it's become now a one-time BLS signature, you can publish only one decryption key per this value B, per this shift B. And this shift B must be different because otherwise it's like there's no security. Like you can generate signatures out of like as the adversary. And then you can publish one decryption key per value B, and there should be a unique value B per block, meaning you can publish only one decryption key per block identity. So that's what I call the epoch. So there are epochs, and then when you're encrypting, you also take this epoch that you want to encrypt to as the client. And then when you are doing pre-decryption and obtaining the decryption key, you also obtain a decryption key per epoch, and a single decryption key can be posted per epoch, which means sent a transaction encrypted for some epoch 1, meaning for block 1, and too bad my transaction didn't get into block 1. Now my transaction has mempool privacy. No one can decrypt it while it's in the mempool, but no one can include it in future blocks either. So I need to resend my transaction if I want it to be included in the future. So this was the limitation of these earlier works with epochs. So I know that this might be a lot, so please ask questions if anything is unclear.
This is was this idea. Do you have many papers making fun?
I'm taking a very high level, like 1,000 feet summary of them, but so the earliest one to attack this problem of batch decryption was, I think, number 1. And then number 2 and 3 basically propose this. This is like the solution that is similar in both of them. Number 2 and 3 are better. I think the number 1 had still some issues, and then number 2 and 3 solved those issues. And then they have basically this architecture. And number 4 is also another concurrent work. And I think they use a similar architecture, but I'm not so sure. Yeah, but it is a concurrent work with the other ones. Okay, so let's go forward. Okay, well, not all hope is lost. So today we will see batch decryption scheme without this epoch limitation, meaning that you will be able to encrypt your transaction and it will be able to be included in any block. Like there will be no like tying to a specific block or epoch ID. Okay, so now as a warm-up, let's design very quickly an epoch-less, epoch-free batch decryption scheme using a very heavy hammer called attribute-based encryption. Okay, so what is attribute-based encryption? It is an even fancier public key type scheme where, again, there are like 4 algorithms. There's a setup with the master public key and secret key. When I'm encrypting, I will be encrypting not under an identity, but an attribute, okay? And when I'm deriving, I will be deriving a secret key for a circuit that takes attributes as input. And now I will be able to decrypt the ciphertext created under an attribute if I am given a secret key for a circuit such that the circuit applied to this attribute is equal to 1. This is basically like an access structure for decrypting ciphertext. Okay, so this is the main primitive, and again, security, again, informally says messages encrypted under some attribute should remain hidden if no secret key for a circuit such that the circuit applied to this attribute outputs yes was published.
Wait, what's C?
C is a circuit. It's a circuit that takes attributes as input and outputs 0 or 1.
Oh, wait, now you're talking about something else.
Yeah, this is attribute-based encryption. So I will basically be using this heavy hammer as to design epoch-less batch decryption as a warm-up to show that this is possible. Okay, so is the ABE primitive clear what it's doing? It's even fancier than IBE in the sense that secret keys are for circuits, and you can use this secret key to decrypt if that circuit actually approves your attribute. Okay, so here's how you can easily get a batch decryption from ABE. So for the public parameter and the secret key of the batch decryption, you simply return the master public key and master secret key of the ABE scheme. For encrypting under an identity, now we're going to treat our identities as attributes. You simply invoke the encryption algorithm of the ABE under this identity. For deriving the decryption key for our batch, I will be deriving a secret key for a special circuit. But what is this special circuit? The special circuit is a circuit that outputs 1, approves if and only if an identity is inside the batch that characterizes this circuit, okay? And decryption works as follows. It's, again, this ABE decryption. And that's pretty much it. Yeah.
What is the second input to setup? Like, is that some class of circuits that you can actually?
Yeah, exactly. I glossed over that, but yes, you typically characterize it with a class of circuits.
And so this type of circuit is, like, you can actually construct ABE for this type of circuit?
Yeah, this is like a simple circuit. You can imagine it like basically imagine my access is not 1 but 0. I want it to be output 0. It can just be like input minus R1 times input minus R2. So you can yeah, you can definitely do that. There has been ABEs not only for Boolean circuits but also like arithmetic circuits. So and then now the important thing to notice is that these ABE secret keys or this ABE secret keys, which is going to be our decryption key, is succinct. It is even in like the earliest ABE schemes, this only scales like, let's say, quadratically in the depth of the circuit, and the depth of the circuit could be logarithmic in the size of the batch. So it is succinct in the batch. And there are newer ABEs where this is actually constant, well, scaling only in the security parameter size. Okay, so now we did get a essentially an epoch-less batch decryption scheme from our ABE. Okay, so are we done? Now we get like a batch decryption from ABE. Like, should the talk end here? I would argue no, because of the following reason. We would like to achieve as succinct parameter sizes as possible. And let's look at what the batch decryption scheme derived from ABEs do when it comes to parameter sizes. Okay, so the special flavor of ABE that I described is called KP-ABE, it's key policy attribute-based encryption. And you can build this from lattices, and their security relies on the learning with errors assumption. And their attribute spaces, let's say, has size k, like k bits. Now, if this is the case, and let's suppose you use the technique we just saw on the previous slide to design batch decryption from these KP-ABEs, what would be the size of your ciphertext, let's say, right? So PK is the size of the, not the attribute or anything, it's the size of the public parameters of the batch decryption scheme. SBK is the size of the decryption key of the batch decryption scheme, and CT is the size of the ciphertext of the batch decryption scheme. Okay, and if you use KP-ABEs to design a batch decryption scheme, these are the sizes that you would get. Right, so here you can see that PK and CT scale linearly in this K. And if you don't want collusions in these identities when clients encrypt their transactions, you need to pick this K to be large. Okay, so this is one line of work. You can use one idea you can use to get batch decryption. Now there's this amazing prior work called Beat MEV. And in my mind, I think they got the first practical batch decryption scheme without epochs. This scheme relies on pairings. It relies on a really smart use of these key-homomorphic puncturable PRFs. Their parameter sizes look as follows. So the decryption key and the ciphertext size are essentially constant. Well, okay, there's a caveat here, but I'm gonna gloss over that for now. They are really small. They are practically small, but their public key size is quadratic in the size of the batch. Sorry, not the public keys, the public parameter size. PK is the public parameters of our scheme. Like you can think of it as the master public key of the scheme. It is quadratic in the batch size, but there is a bigger issue than this slightly larger public parameters, which might practically be still not too large. The issue is there is a easier censorship attack Beat MEV, because in Beat MEV, it does not really fit into this batch IBE paradigm per se, but when there is a encryption going on as a client, when you send your transaction to the chain, you basically do it for a position in these all possible places in the block, right? Now, this makes it easier for an attacker to censor you, because if they get this position, and then your transaction is not going to make it. One transaction can get in per position. Whereas in the KP-ABE based solution, if I want to really censor you, I need to fill up all the positions in the block. So if you model this in an economic way, it will be the cost of kicking out one transaction for a given position versus kicking out everything inside the block. So that is why I would say there's an easier censorship attack on it. So what I mean by that is,
Why is
Well, okay, so there is still a gap between, so suppose there are positions in the block and I encrypted my transaction for a given position. There is still, now in the earlier case, the adversary just needs to somehow get a ciphertext that it created for that position to basically prevent mine from getting into the blockchain. Versus in the other one, it needs to fill up all the positions to specifically target.
understand?
Uh,
I thought KP-ABE, you just encrypt to some random identity.
Okay, so this is like, okay, so this economic argument is a way to basically argue why it would, what I mean by this easy censorship attack. So in the KP-ABE case, everyone picks their random identities and send them. And then now a block can be created with that, but I don't enshrine a position in the block for my transaction. Like it could be anywhere in the block. So now if the adversary really doesn't want my transaction to get in, it basically need, like for any position that it can get any position my transaction get in, the adversary needs to somehow send its own transaction to block that point.
I guess maybe my question is like your description of the KP-ABE scheme doesn't have position in it, so I don't understand why this has to do with position at all.
Yeah, so in the KP-ABE case, there is no position. In the beat-MEV case, there is a position. So in beat-MEV, I encrypt my transaction to, in some sense, a position or like a special ID from 1 to L in the block.
Okay, so basically each and EV there's position and KP-ABE there's no position. That's
Yeah, that's the point.
Is the position just for like one epoch, or is it like the adversary needs to like prevent your position from getting included in all the epochs, following epochs?
So no, so if I want my transaction to be getting into this specific block, adversary needs to target that position in that specific block, but my transaction can still get into the next block. If the adversary doesn't want it, then it needs to target the position in the next block and the next block again. Yeah.
So for KP-ABE, it means the adversary needs to like target all the transactions in all the future blocks.
In the KP-ABE, I think, okay, so let's ignore the economic line of reasoning. Let's think of it this way. In beat-MEV, there is a position that I pick to encrypt my transaction to, and then I send it to the mempool with that. In KP-ABE, there is no position. In KP-ABE, there is more flexibility as a result to reorder transactions. Okay, so that's the difference. So in our scheme, we again design it from, so our scheme, so we will, okay, what is our scheme? So we will be designing a new scheme for batch decryption from lattices. Security will rely on learning with errors assumption. And our scheme will have a parameter that is beta, that is tunable. And in our scheme, if you set your beta to be 1, then you basically get these types of parameter sizes. As you can see, there is no dependence on like this K, which is the attribute space size as was in the KP-ABEs. And if you set beta to be K, then there is this dependence. Now you might ask, why would you ever set beta to be K? It's because of this position issue. So if you set beta equals 1, our scheme is as vulnerable to censorship as beat-MEV in the sense that, again, you will be implicitly enshrining a position for your transaction. Whereas if you set beta to be K, then you won't be enshrining a position for your transaction. So in that sense, it's flexible and you can pick any K you want.
So are you more practical than that? It seems like it's like incomparable.
It's not more practical because our scheme is again based on lattices. Beat-MEV in practical terms, if I like actually write how many bits it is going to be more practical.
And then what's the assumption for the beat-MEV?
I am not so sure. I think the assumption goes into the construction of the Q-homomorphic puncturable PRF. Yeah, it's based on pairings. I don't remember the exact assumption. Maybe CDH, not sure. Co-CDH. Yeah, I need to double check.
Is it LWE or bilinear?
It's bilinear groups. No, it's not LW in beta maybe. Yeah, it's bilinear groups. Yeah, so yeah, in that sense, it's incomparable. Well, we can claim plausible post-quantum, but I think our goal was to basically design this tunable the scheme with a tunable parameter that can span this region. And also, we did not want to use a heavy hammer like KP-ABE, but design it from first principles, hoping that it will be more efficient if it comes to implementation compared to KP-ABEs, but we don't have any data on that yet. Okay, so now let me describe what our Epochs batch decryption scheme does. So at a high level, it actually follows the same paradigm as these batch decryption scheme with epochs. So
In practice, it is just sending decryption shares. Is that not a practical solution? Because I don't think L is that large. I mean, N may not be that large either.
yeah, if N and L are not that large, that's a practical solution.
Sure, that actually can be true.
Yeah, that could actually be practical depending on what the L is. I agree. Especially like in a blockchain, maybe there will be like a small part of it from the encrypted mempool, and there is a part that is where people are okay with the transaction being public. If the part for the encrypted mempool is small, you are totally right there. That L is small, so it could be a practical thing. But I guess like part of my goal is not only to describe our specific work in that sense, but also to lay out the landscape of what is possible and what is the trade-offs in all of those.
Just a quick question. So for the PK, the like public parameter, is it like reusable or like how?
Yeah, that is like just done once at the beginning.
Nice.
It's reusable. Yeah, maybe we should call it PP. The PKs you should think of it as PP. Okay, so our epoch batch decryption scheme. Well, part of the trouble part of the reason why I went to this trouble of explaining all this batch decryption with epochs is because we follow a similar framework as them. So if you recall, they were combining an identity-based encryption scheme with a polynomial commitment scheme, or like a commitment to a batch of identities, right? We will be doing essentially the same thing. We will be combining a lattice-based, identity-based encryption scheme that is ABB10, Agarwal, Boneboy, 2010. And then in lieu of the KZG commitments for committing to a batch of identities, we will be using this new object by Waters VMW 2024, shifted multi-pre-image trapdoor sampler. And this is like quite a bit of words, but you can actually build a lattice-based vector commitments from shifted multi-preimage trapdoor sampler. And our decryption key, again, will basically be the signature scheme defined by the ABB10 IBA. But now the signature is going to be on a batch of identities, just like in these earlier works, right? And then how do you generate this signature on a batch of identities instead of a single identity? That's exactly the part we will be using the multi-preimage trapdoor sampler. So I underline this term multi-preimage because we are now generating a signature on a batch of identities, meaning in the original ABB10, your signature is like if you treat your signature as a preimage of one thing, here is a preimage of multiple things. So that's why it's multi-preimage trapdoor sampler. And then instead of for encryption, we are not going to use like this witness encryption for a linear constraint system, but we are going to use whatever encryption the ABB10 IBE uses, which is dual regev. Okay, so this is the blueprint of the whole construction. So now I have, I think, 15 more minutes so that I can go over the construction a bit. But to actually explain the construction, I need to explain what ABB10 does and what the shifted multi-preimage trapdoor sampler does. And so I will start with those.
Yeah, so the room is booked till 6. So
Oh, okay. Okay, yeah, I can go on as long as you go on. Oh, and of course, our batch decryption scheme is correct, and given the LWE assumption, it is selectively secure in the random oracle model. So I can also go over the proof if there's interest afterwards. Okay, so what is the shifted multi-preimage trapdoor sampler does? Okay, so let G be our gadget matrix. So this shifted preimage trapdoor sampler, I'll just refer to it as a trapdoor sampler going forward, is characterized by 3 algorithms. The first one is, let's say, CRS generation algorithm. It basically samples 2 uniformly random matrices and outputs them. That's it. Here, R is like randomness, but you can ignore that. Then there is a special expand algorithm. Now that's the heart of the matter in some sense. It takes this CRS and it takes a sequence of L bit strings, okay? Each bit string is size beta times log L, okay? So this part here, ignore the M and then this M, this beta times log L is the size of each bit string, and there are like L of them. So as you can see, the beta parameter that I was making a big fuss about, it already enters here into the picture in the trapdoor sampler. Okay, now what this algorithm does is it constructs these matrices AUI, given a UI. Okay, then it constructs this large, huge matrix A. Then using the gadget matrices trapdoor, it obtains a trapdoor for this large matrix A. Okay, you don't need any secret for this. Like you can just do this this trapdoor sampling operation for this large matrix A. Okay, and then it outputs basically these matrices it found for each of these bit strings UI and the trapdoor for this large matrix A. UI is basically input to the expand algorithm. It's like a bit string.
In the final scheme.
In the final scheme, UI is gonna be part of the identity. It's not gonna be the identity itself, but it will be derived from the identity. So in the final scheme, I will use the identity in 2 ways. First, I'm gonna hash the identity to find UIs, and then I will also use the identity in the ABB10 IBE scheme. So here, there's a beta term, right? If I set beta equals 1, when I hash this identity and find a UI can only take L possible values because it's of length log L. So that is why in that case, I will essentially be enshrining a position in the block. So you can think of the UI as a position in the block, but if I set the UI to be large, like beta times log L, like it's very hard to find a collision in this position, and then I only have like L of these in like huge number of positions filled per block. You should think of it this way. Like if I set beta to be 1, then my size of my total number of positions actually shrinks to the actual size of the block. Then I have potentially many collisions, and then I have like more position enshrining. Okay, so here, okay, so like let's go forward. So this is what the expand algorithm does. And then now how do you sample the trapdoor? You basically call the sample pre-algorithm from the lattice literature, and you sample this vector. So what the sample pre does is, this vector is essentially a Gaussian vector with a Gaussian width parameter sigma conditioned on the fact that it satisfies this equation. Because if you notice, the sample pre takes this large matrix, right? And then it takes this target vector and it samples this, and then the sampled vector needs to satisfy this equation.
Does it matter what those T are? Does the T matter then?
Which T?
The small T on the right hand.
These T?
Yes.
It matters because you are essentially, what sample pre does is it essentially samples a pre-image of this T vector under this matrix.
Okay.
So that's why it needs to go. Oh, you're saying like, does it need to have a special structure, this T? No.
So any T will.
Yeah, any T will work. Yeah. It doesn't have to have a special structure. Now, if you open this large matrix vector product, you obtain that this matrix vector product implies this equation for each L. Okay, now I think the name will start making more sense. First of all, we did sample the scheme did sample a trapdoor. Right, this TA was the trapdoor, and this trapdoor enables you to sample multiple pre-images V1 through VL, and it's shifted because it's all shifted by this common G times C hat term. So let's call this G times C hat term just regular C, ignore the C hat. So now all of these pre-images essentially are shifted by the C term. This C basically acts like a binder, like I'm binding these multiple things using the same C. In another sense, you can design a lattice-based vector commitment out of this, because imagine your TI is essentially a one hot vector. Okay, so and you want to commit a bunch of integers. You basically set your TI to be my integer times the one hot vector, and then I use this shifted multi-preimage trapdoor sampler for all these TIs, right? Then this C is going to be the vector commitment in some sense, and VI is going to be the opening proof. So that's kind of like a powerful object. Okay, the second primitive we are going to use in our construction is the explainable sampling algorithms. They go into this IBE scheme. So the first one is sample left. It basically takes a long input and then it deterministically outputs a vector V. Why is it deterministic? Because I'm fixing the randomness. I'm giving the random bits to this otherwise randomized algorithm explicitly. And then what it does is essentially it takes a matrix A, a matrix M1, a trapdoor for the matrix A, a gadget trapdoor, a target vector U, and a Gaussian width parameter. It samples a pre-image vector V, such that the sampled pre-image vector V is, sorry, this should be not computational, but I think statistical indistinguishable from basically a Gaussian vector V that satisfies this expression. Okay, so now I'm basically using this sample left to sample this V value. But now what is special about sample left is that I don't need the trapdoor for all of this huge matrix. I only need the trapdoor for A. I don't need the trapdoor for M1. Okay, so this is what sample left does. That's why it's left, because I only need the trapdoor for the left side. Now this is explainable because I explicitly input the random bits, meaning that it's associated with an explain algorithm, which does the following. You just give the inputs of the sample left and the potential output of it some V, and it tells you what random bits you used to get this V. So it's explainable in that sense. It's up to a certain precision. And we designed this. I think in Zoom it gets blocked out, these references. But yeah, so this explainable sample left algorithm easily follows from some earlier work. So the first earlier work, they did an explainable sample pre algorithm, the sample pre, the pre-image sampling algorithm we have seen. And then the even earlier one did like a sample explainable Gaussian vector sampling. So follows from those. Okay. Now there's also a sample right. What sample right does is it takes a matrix AB, short matrix R, now a trapdoor for B for the right-hand side, and a target vector U, and it basically samples the pre-image V for this relation here, the red part. So U was our target vector, right? Now I use the trapdoor for B, not A, to basically generate this vector V. That's why sample right, the trapdoor is now on the right-hand side. Okay, so these are some sampling algorithms. We don't need the sample right to be explainable in our scheme. Okay, so now how are we going to use the sample left for this ABB10 identity-based encryption scheme? Well, before I get to that, let me first recap this hash function this IBE scheme uses, which is this hash with full rank differences. What it says is that if you take the difference of the hash of two different identities, it needs to be full rank. That is what it says. Like the hash function outputs a matrix, and the difference of two different hash evaluations needs to be a full rank matrix. That is the hash function. Okay, so the IBE scheme is going to use this hash function, but for setup, it's not too complicated. It samples these random matrices and vector, A tilde, B tilde, and U, and it also samples uniformly random looking matrix A along with a gadget trapdoor for this matrix A. Okay, so and the gadget trapdoor is the master secret key, and the rest is the master public key. Okay, so now keygen is tricky. So what it does is does the following. So I'm giving this identity. Sorry, this should be called derive. I overused some or underused the notation. So this is derive, not keygen in the notation of our talk. So I'm going to derive a secret key for this identity R. To do that, what I do is that I use the sample left algorithm to derive a secret key here. If we just focus on the red part at the bottom, such that if the secret key is multiplied by this matrix, it gives you this target vector. So I sample such a short vector, a short preimage vector. Are there any questions on what the keygen is doing? It's calling sample left to sample this short preimage vector. So how am I tying this to the identity? As you might notice, this matrix has A on the left side, but it's A tilde plus HFRD B tilde on the right side. So the identity enters into the picture here. Now encryption is the dual regev encryption using the public key U and the public parameters this matrix. Now you might notice that this matrix is the same matrix we used in generating this preimage for key derivation for the identity R, right? Okay, so this is how I encrypt my transaction. And for decryption, I just do this. I round up the term inside this round function. Now, why is this correct? Maybe that will make more sense. Now let's look into what goes on inside this round function. What is CT1? It's simply this, right? I just copied over at the bottom here. Now, what is CT2? It's this whole thing, but I'm now multiplying it with this short vector, short preimage vector, right? So that's exactly what I did here. Now, let's group the terms that depend on this secret random S. Okay, so the S is here, and this is the terms that are multiplied with S. Now, if I go back one slide, notice that this secret key satisfies this expression. Now, what does this mean? What is this term inside here? Is 0, right? So S cancels out, disappears. Now, epsilon1 is an error term. SKR is a short vector. Epsilon is an error term, so these are really small. So all I'm left with is roughly m times q over 2. So that's why I rounded up to get rid of these short contributions. And then from that, I can recover what m is. Okay. There is devil is of course in the details, and this is an amazing paper. There are lots of smart ideas that how you use sample right to simulate secret keys, but we don't need to cover them all today. Okay, now our scheme is literally going to be tying the trapdoor sampler with the IBE. So as a result, the setup is just going to be the setup for the trapdoor sampler and the IBE. So we just run the setup for the trapdoor sampler. Then we generate these matrices as in the IBE. Now we do something special that is not done by any of the other two schemes, which is we sample this randomly looking matrix C along with a gadget trapdoor. Okay, so this is done because this will be used to derive the decryption key. And we return this gadget trapdoor for this matrix C as part of the secret key, the master secret key. And the public parameters are these. Okay. So this is our setup. It's basically the setup of the trapdoor sampler, setup of the IBE, plus this matrix C with the gadget trapdoor. Okay, so how does the keygen or pre-decryption work? How do we get the decryption key? So, well, as I was saying, we first hash the identities to get these bit vectors that were called UI. Now they are called H tilde I. Okay, so then now these need to be distinct, otherwise the pre-decryption algorithm just fails. Then you run the expand algorithm from the trapdoor sampler. Recall that this TD contains the trapdoor for the matrix A that is written here. Okay. So you simply run the trapdoor sampler's expansion algorithm with these bit strings. Then you also construct this A tilde prime like this, and then you construct this target vector U. So if you look at just one row of these matrices, like this one row essentially looks like what I was doing in the ABB10 IBE, right? In the ABB10 IBE, I had this matrix with A dash like A tilde plus like HFRD B tilde. So now each row is essentially contains like one matrix of the ABB10 IBE scheme. But now it's not just one row, but these are all full matrices. Okay. So now I fix the randomness because I'm going to call sample left. And to fix the randomness, I use this HS hash function modeled as a random oracle. And then why do I fix the randomness? Because I want decryption to obtain the exact same values in the sampling. That's why I need to fix the randomness. Now I call sample left on this A tilde prime using the trapdoor for the matrix A and the target vector. Okay, let me go back quickly. So these matrices are the things I'm gonna call sample left on. And now if you focus on each row, what sample left outputs is a large sequence of vectors. And for each index I from 1 to L, these vectors satisfy these equations. Okay, so these equations look almost exactly like the ABB10 IBE, except I have this shift here, right? Due to this C hat, due to this G. So that is why I was using this shifted multi-preimage trapdoor sampler, because I do want this shift. This shift is tying all of the things inside my batch together. And this shift is what I'm going to use to generate my decryption key, because my decryption key will be a preimage of this shift under this matrix C that I generated. So, and then this means that the decryption key times C is simply this shift. Okay. Are there any questions on what pre-decryption algorithm does? It is basically ABB10 IBE pre-decryption, except I do it for like all these L things together, but except also that I tie all of these things together with this common shift. And that is why I can't just use sample left immediately. I need to use this multi-preimage, shifted multi-preimage trapdoor sampler. Okay, so like here, the C hat is like a commitment to all the identities in the batch, and you can think of this VI1, VI2 as like the opening proof for each identity in the batch. And then encrypt is gonna be, again, getting the same H tildes, like same bit strings. There's this local expansion algorithm of the trapdoor sampler. It just, instead of giving this full matrix A and its trapdoor, it's just giving you one simple matrix inside this full matrix A, like one simple ARI. And now the encryption is again dual regel, just like in the ABB10 IBE, except I have this extra term for the shift. Okay. So if you look at this first term and the third term, they're exactly like the ABB10 IBE, except that I have now also this middle term, which is the shift.
Wait, this shift on a high level offers the same goal as the one-time pad shift in the prior works you perceived?
it offers the same goal as the KZG commitment. The one-time pad was more like, oh wait, so you mean like this B term, this one-time signature thing? Which one?
I think previously you mentioned like lots of prior works, they have a like shift for every transaction.
Oh, yeah, that's a separate shift. No, it's a separate. This shift, you should think of it as the KZG commitment in those works. That's the analogy. That other shift that you are mentioning it's more of a drawback than a plus in some sense.
Let's check that.
Yes. Yeah. That like if you had this hash operation to be linear, well, then it won't be modelable as a random oracle. Then you wouldn't have this shift. But yeah, that. Yeah, and then okay, so we have seen the encryption. Decryption does almost the same things as the pre-decryption. Like whatever we were doing for key generation, we are doing it for the decryption. We are getting these bit strings. We are expanding these bit strings to get these ARIs. We are finding you're using the random oracle to find the random bits that are used in sample left. Now you can see why we had needed this random oracle in our construction, because if everyone just picked their own randomness in the decryption, like each individual person picked their own randomness for decryption, and the guy who generated the decryption key also picked their own randomness, then we would all end up with different vectors. So like this would not work. So we don't want us to end up with different vectors. So I'm basically making the randomness common. And we again use sample left to get all of these. To do all of these steps, you actually don't need the decryption key, right? The decryption key only comes in when you are worried about the middle term of the ciphertext, because the decryption key is essentially the preimage of this shift small c under this C matrix. Okay, so now let's see the correctness again. Let's analyze it. So TT1 is these first three terms. Okay, so the decryption key times CT2 is these two middle terms. And this VI is the opening proofs, the so-called opening proofs times CT3 is this term here. Now I again group everything in front of S into one large term. Okay, now what is the value of this thing? Well, I think we have observed something here. The value of that thing is actually 0 because of what sample left gives us here. And now because this is 0 and E1 epsilon 1 is small, this is noise term. The decryption key is small, it's a short vector, so this is small. These are short vectors, again this is small, and again I'm on the left with M. So that is how I do the decryption. Okay, so that brings us to the end. So we talked about epochs and also batch decryption schemes with succinct parameters, ciphertexts, and secret keys. And then you can check out the paper for more on an optimal construction based on trilinear maps, which don't think exist yet. Then basically a lattice version of beat MEV. We did not write it very formally, but we basically show how you can take the beat MEV construction and make it a lattice-based. Then how to thresholdize the decryption key, because yeah, and then how do you encrypt multiple bits, because so far the batch decryption scheme was encrypting a single bit, and also how to get adaptive security. Because the validators are publishing the decryption key, right? I would like it such that the decryption key is thresholdized, and then if T out of N validators publish their share of the decryption key is generated in the blockchain application.
Oh, I see. This is just like the encryption scheme itself, the key will be sequence share.
Yeah, exactly. So this is much more, it's like much more notoriously harder for lattices than pairing-based constructions. So when I said find more details in the paper on thresholdizing decryption key, what we talk about is two ways you can do this. The first one is a naive way where I can secret share it, and then now this is not a not so efficient thresholdizing method. There is a paper, like I think 2010 or 11, by Bandlin et al., where they show how to generate pre-images from thresholdized gadget trapdoors for lattices. So that scheme could be used in our case because our secret key, our decryption key, is essentially pre-image. But here, that scheme requires a trusted setup. And then the online phase is quite efficient. It's non-interactive, but the trusted setup is pretty involved. And if you want to get away from trusted setup to a DKG type scheme, then it becomes very complicated as far as I could understand.
I mean, there's always, you can always do, what about this universal thresholdizer?
Yeah, that could be possible. Yeah, maybe.
Maybe not very efficient.
Yeah.